Have you ever looked up at the night sky and wondered where it all came from? How did the stars, how did the planets, how did our home Earth come to be? This is one of the biggest questions we can ask. The answer is a grand story, a cosmic tale that stretches across billions of years. It is a story of creation. It is a story of change. It is a story of connection. It starts with a single point, smaller than an atom, then unfolds into the vast, glittering universe we see today. This journey from an unbelievably hot, dense beginning to the familiar worlds we know, and it's a story science allows us to tell. The universe did not always look like this. There were no stars, there were no galaxies, there were no planets. Everything we see, and everything we are, was born from a long, epic process. This story begins with the Big Bang, a moment of incredible energy and expansion. From there, simple particles formed. Those particles came together to build the first atoms. Our story begins at the very first moment, a point in time we call the Big Bang. About 13.8 billion years ago. All energy, all of space itself, was squeezed into a single point of unimaginable heat and density. For the next several 100,000 years, the universe continued its relentless expansion. As it grew larger, it also grew colder. The temperature dropped from billions of degrees to just a few thousand, similar to the surface of a star. This cooling was a critical turning point. The frantic energy that had kept particles from binding together was finally starting to fade. The cosmic game of musical chairs was slowing down, and the particles were getting ready to find their partners. The universe was on the verge of a dramatic transformation, from an opaque fog to a transparent space. This pivotal moment, which happened around 380,000 years after the Big Bang, is called recombination. Those tiny temperature differences seen in the cosmic microwave background were the key to everything that followed. The slightly hotter spots were regions where matter was just a tiny bit less dense, while the slightly colder spots were where matter was a tiny bit more dense. Think of it like a perfectly smooth sandbox with just a few extra grains of sand piled up in certain places. But there was another key ingredient at play: dark matter. This is a mysterious, invisible substance that makes up about 85% of all matter in the universe. We cannot see it or touch it, but we know it is there because we can detect its gravitational pull on the things we can see, like stars and galaxies. Dark matter began to clump together even before recombination, because it does not interact with light. After the universe became transparent, normal matter, the newly formed hydrogen and helium atoms, began to fall into these gravity wells created by the dark matter. Imagine dark matter as an invisible scaffolding, erected in the early universe. Within the dense filaments of the cosmic web, the invisible scaffolding of dark matter had gathered enormous, roughly spherical clouds. We call these structures dark matter halos. They were the largest and densest clumps of matter in the young universe, and they acted as cosmic cradles. The hydrogen and the helium gas that had been flowing along the cosmic web was now being pulled deep into the centers of these halos, becoming more and more concentrated. These were the seeds of the very first galaxies. These earliest structures were not the grand spiral galaxies we see today. They were much smaller, what we might call proto-galaxies or dwarf galaxies. They contained only a fraction of the stars of our modern Milky Way, perhaps only 1 million or so, compared to the hundreds of billions in our own galaxy. But they were incredibly important because they were the first places where the conditions became right for stars to form. Inside these small, dense halos, the accumulated gas began to cool down and collapse under its own immense gravity, triggering the birth of the very first generation of stars and ending the cosmic dark ages. Galaxies do not grow in isolation. Just as gravity pulled together the first halos, it also pulled these halos toward each other. The cosmic web was not a static network. It was a dynamic system of gravitational highways. When two of these halos got close enough, their mutual gravitational pull would become irresistible. They would begin a long, slow dance, orbiting each other, getting closer and closer with each pass, until they finally collided and merged into one. This process is called galactic merger. When two galaxies merge, their clouds of gas slam into each other, triggering a massive burst of star formation. Our own Milky Way galaxy has grown this way for billions of years. As galaxies grew larger through mergers, something remarkable began to happen to the gas within them. This sinking and settling process naturally creates a spinning disk. Think about water going down a drain. As it gets pulled toward the center, any small amount of rotation it has gets amplified. This process formed the iconic, flat, rotating structure we call the galactic disk. Within the spinning disks of galaxies like our Milky Way lie vast, cold, and dark clouds of gas and tiny specks of dust. These are called molecular clouds, and they are the cosmic nurseries where new stars are born. For a star to be born, a part of one of these giant clouds must begin to collapse under its own weight, a process set in motion by the relentless pull of gravity. As the chosen clump of gas collapses, it does not fall together into a single giant star. Instead, the cloud breaks apart into many smaller, denser fragments. Each of these collapsing fragments continues to shrink, pulling in more and more gas and dust from its immediate surroundings. When the core finally reaches 15 million degrees Celsius, nuclear fusion begins. Once a star is born, its core becomes a cosmic factory, a stellar forge for creating new elements. Oxygen we breathe, carbon in our cells, silicon in the rocks beneath our feet were not created in the Big Bang. They were forged deep inside the fiery hearts of stars. When these stars died, especially in the titanic explosions of supernovae, they scattered these precious new elements across space. As a young protostar is born from a collapsing gas cloud, not all the material falls directly into the star. A significant portion settles into a flat, spinning pancake around the star's equator. The disk is not uniform, hotter and denser near the star, progressively colder and thinner farther out. That creates the frost line, the snow line. Inside this line, it's too warm for volatile compounds like water, ammonia, and methane to freeze. First step, microscopic dust grains start sticking together. Gentle collisions clump grains like dust bunnies. Over thousands of years, this coagulation slowly builds larger particles. The smooth disk becomes a swarm of solid, rocky, icy bodies. The process of growing from planetesimals into planets is called accretion. It's a rich-get-richer scenario where the largest planetesimals have the strongest gravity and therefore grow the fastest. In the hot inner part of the disk, inside the frost line, this process builds up planets from rock and metal, like Mercury, Venus, Earth, and Mars. Beyond the frost line, protoplanets can grow much larger, much faster. Once a core becomes massive enough, it begins to pull in huge amounts of hydrogen and helium gas. This is how gas giants like Jupiter and Saturn are born. After tens of millions of years, the planet formation process is mostly complete. What is left is a stable, mature solar system. Our cosmic story has taken us on an immense journey, spanning 13.8 billion years, from the dawn of time to the birth of worlds like our own. We have seen how the entire universe emerged from a single, hot, dense point in the Big Bang. As it expanded and cooled, hydrogen and helium formed. Inside galaxies, stars became cosmic forges, transforming simple elements into heavier materials essential for life and planets. When these stars died, they scattered these precious elements across space. Every atom in our bodies was forged in the heart of a distant, long-dead star. Understanding this grand narrative does more than satisfy our curiosity. It connects us to the cosmos. It reveals that we are not isolated observers, but an integral part of an ongoing creative process. As we continue to explore the stars and the worlds around them, we are not just looking out into the void. We are looking back at our own origins, seeking to understand the remarkable chain of events that allowed a planet like Earth and life like us to exist.